This lesson is on polygon angles and diagonals of a polygon. An angle is formed by a vertex or point and two rays that make the arms. We measure the angle between the arms in degrees to show how open it is. There are lots of ways that we can describe angles. We already know about acute angles, right angles, and obtuse angles. Today we'll learn about central, straight, and reflex angles, complementary and supplementary angles, and interior and exterior angles. A central angle is an angle with its vertex at the center of a circle or the center of a polygon. If we add up all of the central angles in a figure, it always equals 360 degrees. Think about turning yourself all the way around 360 degrees. You've just spanned the entire central angle. A straight angle measures 180 degrees and looks like a line. We can think about this as nestling two right angles together, noticing that their base makes a straight line of 180 degrees. 90 degrees plus 90 degrees equals 180 degrees. A reflex angle is larger than 180 but less than 360 degrees. In this picture, the quadrilateral has a reflex angle at vertex D. Notice this angle is inside the quadrilateral. Complementary angles are two or more angles whose measures add up to 90 degrees. They may be next to each other, adjacent, or they may be apart from each other in the picture. On the left, we have separate angles, 15 degrees and 75 degrees. Together they make 90 degrees. These are complementary to each other. On the right, we have adjacent angles of 25 degrees and 65 degrees. Together they add up to 90 degrees and form a right angle. These angles are complementary to each other. Supplementary angles are two or more angles which sum to 180 degrees. They may be adjacent or separate. On the left, we see 45 degrees and 135 degrees, adding up to 180 degrees. We notice that the bottom line forms a straight angle, which we know measures 180 degrees. The blue angles on the right, 15 degrees, 85 degrees, and 80 degrees, add up to 180 also. These angles are supplementary to each other. An interior angle of a polygon is formed inside the shape by two adjacent sides. In this pentagon, we see one interior angle marked with measure 108 degrees. A polygon with n sides always has n interior angles. Our pentagon, which has 5 sides, has 5 interior angles. If it was a dodecagon with 12 sides, it would have 12 interior angles. If each interior angle of the polygon is less than 180 degrees, the polygon is always convex. If one or more of those angles is greater than 180 degrees, then the polygon is always concave. Let's look at an applet for interior angles. Here we have a pentagon. In fact, it's a regular pentagon. Notice that each interior angle measures the same, 108 degrees. I'll click off the regular check to see another pentagon. This time you can see interior angles that are all different. We can click on a vertex and drag to change the shape and observe what happens to the interior angles. If I push it in so it's concave, notice we end up with a reflex angle of 230 degrees. An exterior angle of a polygon is the angle outside the figure that's formed between one side of a triangle and the extension of its neighbor side. A polygon with n sides has n exterior angles. In our picture to the right, we have an octagon. Notice it has 8 sides and 8 exterior angles, of which 2 I've shown with red arrows. Let's look at an exterior angle applet. Here again we have a pentagon. Notice that we've taken each side and extended it in one direction and then measured from that extension to the adjacent side to see the exterior angles. Again, we can click on a vertex and stretch and bend the shape and observe what happens to the exterior angles. If I push it in and make it concave, notice we get a negative exterior angle because we bent it the wrong way. I can actually change the pentagon shape to more sides, and you can see this heptagon or 7-sided polygon also has 7 exterior angles. This particular applet also allows you to switch directions of the extensions or change it back to regular. The sum of the interior angles of a polygon is found by adding up all the measures of the interior angles inside the shape. The sum of the interior angles of a triangle is always 180 degrees. Now, if we switch it to a quadrilateral, it's going to be a different, larger sum. A pentagon would be a larger sum than that. But let's go back to triangle. We're all convinced it's 180 degrees, but how can we prove it? Here are two very simple proofs, both visual and hands-on, that can show that a triangle always has an interior angle sum of 180 degrees. Listen to this young man.
Hi, I'm here to prove that the sum of the interior angles in a triangle is 180 degrees. Here is a triangle whose angles marked A, B, and C. Join angle A and B together so that they form on a straight line. Follow angle C to meet angles A and B at a point. Since the sum of the angles of a triangle, when placed adjacent to each other, forms a straight line, and the angle of a straight line is 180 degrees, the sum of the interior angles in a triangle must be 180 degrees. Thank you.
Well, did you believe him and his little proof? If not, here's a second proof. I'm going to turn off the noise because it's very loud music, and you can just watch this hands-on activity. Here we've taken any triangle, torn off the corners, lined up the angles adjacent in any order you want, and notice they always match a straight line. Here is proof of 180 degrees of the interior angles of a triangle. Now, the sum of the exterior angles of a triangle is found by adding up all the measures of the exterior angles. The sum of the exterior angles of a polygon is 360 degrees no matter which polygon we're looking at. This seems counterintuitive. If the interior angles sums get larger and larger the more sides of a polygon, why are the exterior angles still stuck at 360 degrees? Well, here's a simple visual proof of what might be going on. Here we see a hexagon with exterior angles marked. We are going to use this interactive yellow box to create our own polygon with exterior angles, and then we're going to shrink it. We're going to scale it down or shrink it over and over and watch what happens. So as I make my polygon smaller and smaller and smaller till it shrinks to a point, now the pink arcs show us that the exterior angles turned into the measure of a central angle, or all the way around, or 360 degrees. This does not matter which shape we use. If we shrink it to a point, the exterior angles end up being the circle and measure 360 degrees. Now, the diagonal of a polygon is a line segment that it connects any two non-adjacent vertices, or it's a line from point to point that falls inside the polygon. Now notice if we trace two adjacent or neighbor vertices, we're actually tracing over the side of the polygon. That doesn't count as a diagonal. If the polygon is convex, then all of the diagonals fall inside the polygon, like this picture. But if the polygon is concave, like this L-shaped figure, then some of the diagonals fall outside the polygon. Tomorrow in class, we will be doing activities for angles and diagonals of polygons.